Okay, good. Thank you for that. All right, so it looks like we got a solution. So let's see if this works. I appreciate that. That's good advice. Thank you. All right, so let's start from the beginning and see if it works. Put a thumbs up if you hear it.
Hi, this is Robin Locke, and this video will give a brief introduction to StatKey,
Yes.
which is a set of browser-based dynamic statistics tools that have been developed for teaching simulation-based methods to introductory statistics students. They are freely available from lock5stat.com and can also be downloaded as a Google Chrome app. The developers are the Lock5 author team, who've recently produced a book called Statistics Unlocking the Power of Data. Here's the team here. And this has just come out now from Wiley as a new book which uses randomization and bootstrap techniques as the foundations for developing inference with students. Program support comes from Rich Sharp at Stanford University, who did a lot of the initial programming, and then Ed Harcourt and Kevin Angstadt, who are at St. Lawrence University, have done a lot of the follow-up work, and it's all programmed in JavaScript. So here's what you'll see as the main StatKey page. Everything runs off of the single page here. And so let me just give you a quick orientation to what's here, and then we'll delve into some of the individual parts. The descriptive statistics and graphics section is standard procedures for displaying results for single categorical or quantitative variables, as well as relationships between pairs of variables, both graphically and with summary statistics. Sampling distributions we've implemented for sampling from a population with getting a mean or a proportion. The heart of the program really comes in the sections on bootstrap confidence intervals for doing bootstrap distributions for single quantitative variables, single categorical variables, differences in means, difference in proportions, and also quantitative relationships. And for all those things, we have a similar set of randomization tests set up in this section over here. We have some replacements for the standard back-of-the-book paper tables to do calculations for normal, t, chi-squared, and f distributions. We've implemented a few slightly more advanced procedures, all by randomization tests for doing chi-square goodness of fit tests for single categorical variables, associations between two categorical variables, one-way ANOVA, and ANOVA for regression. And there's a help button down here which will give you some videos and other support for helping you use StatKey. So that's the basic setup for the whole program. And so let's get in and look and see what it actually does. So we'll switch over to a live StatKey screen here. And let's start with a sampling distribution, something that may be fairly familiar. And let's do a sampling distribution for a mean. We'll pick this option here. Most of the StatKey procedures will start with a little menu item up in the top here, which has a variety of data sets that are pre-built in the StatKey you can choose from. Most of these are tied into the textbook. So let's choose the Stat Grad Schools. This has got some data on the number of statistics students at graduate programs around the country, thinking this is a population. Here's what the actual data looks like. So we've got, I think, 82 statistics programs, and there's all of their enrollment. So we're thinking this is the population. Over here we see a distribution of that population with a mean enrollment of, looks like just over 53, median and standard deviation given there. Okay, and then from this, anything in blue we can sort of edit or use as a button. So we'll start off with the default sample size of 10. Come over here and generate one sample. And pretty consistently in StatKey down here will be our sample window. And so here's a sample size 10. We can see here's the 10 schools that actually got chosen for this particular sample. This is sampling without replacement. Okay, and the mean for this particular sample is 39.3, which shows up here. Okay, if we generate a second sample, this plot changes and we get the new mean displayed in here. We can quickly go to generate 10 samples at a time, 100 samples at a time, or 1,000 samples at a time. And it all goes pretty quickly. So now we've got a pretty good idea of what the sampling distribution looks like for samples of size 10 from this population. And one of the nice features here is as we move the cursor around through the distribution here, each of these sample means that's plotted in the dot plot here relates back to a particular sample that we can see over here. So the StatKey remembers exactly which sample each of the now 1,112 sample means come from. Okay, and so we get a good idea of the picture of the sample means as it shows up there. Now if we want to change the sample size, click on this and say we'd rather have samples size 15. So to generate 1,000 samples of size 15 from this population, we'll click this button here, and we see now the sampling distribution for samples of size 15, and we can compare those, especially comparing things to the standard deviation, to what we saw when we had samples of size 10. So now let's go over and back to the main StatKey page, which we can always get to by going to the icon up here and get back to the main page. So let's move over here to sampling distribution for proportion. And although we do have some examples built in, let's put our own proportion in. So let's suppose we want to sample from a population where the proportion is 0.3. We'll put that in here. And let's change the sample size to 100. We'll choose that here. And so now we generate our one sample. This one got 33 out of 100, so sample proportion of 0.33, which is plotted down here. We can quickly generate 1,000 of these. So now we get a sampling distribution for the proportions, which is centered around 0.3 as we expect. A standard deviation or standard error of the proportions of about 0.045. And again, each of these dots corresponds to a sample count we see over here. What I'm going to do now is reset this plot. So we'll start over again and change over here to the confidence interval option as a display. Here's our population of 0.3 in the middle. And so let's generate our one sample. Here's the sample proportion of 0.32. And the green bars here represent a confidence interval around that proportion of 0.32, which we notice does successfully capture the proportion of 0.3. Here's a second sample, third. So now each of our samples is going to be represented by a confidence interval. And so here's 10 confidence intervals. Who knows one sample proportion of 0.39 did miss the proportion of 0.3 in its interval. So we've got one that's missed so far out of 10. Here's 20, 30, 40. Here's 50. We've got another one that's missed here. So this one's missed on the low side at 0.21. Let's generate a few more. Here's a couple more that have missed. And so out of 100, we've got a total of 92 intervals which successfully captured the proportion of 0.3 and 8 that have missed. And we can see the ones that miss are on the low side here at 0.18, 0.21, 0.20. That corresponds to these values at the low end of the sampling distribution. And the ones that miss on the high end, 0.39, 0.42, 0.46, correspond to these values out here. So those are the ones that miss on either side. So we can get some idea of what the sampling distribution looks like, but also the fact that in the sampling distributions, we see some proportions on the high end and low end, which lead to an interval which misses the true proportion, as we see that. And we could change this if we want to see 90% intervals, okay, which are not quite as successful as we go along there. All right, let's go back to the main StatKey menu now. So one of the difficulties for using sampling distributions in practice is that we really can't generate hundreds and thousands of samples from the same population to see what the distribution looks like. So that's where the idea of a bootstrap confidence interval comes in. So let's look at a bootstrap for a single mean. Okay, and again, we've got several examples built in here. Let's choose Mustang prices. So here's a sample that a student took of prices for used Mustangs, the cars on the web. Has a mean of 15.98, so about 16,000. These are thousands of dollars. About $16,000 is the mean price of the Mustangs. Here's the distribution of the 25 Mustangs in the sample. Now, when we generate one sample as a bootstrap sample, it's going to sample from the original sample with replacement another 25 cars. So notice, for example, this $45,000 car didn't get selected in the sample; needed a $37,000 car, and some of these down here got selected more often. And so the mean for this particular sample is only 13.36. If we generate another sample, we get a new sample down here and a different mean, in this case 16.26. Again, we can do that 10 at a time, 100 at a time, or 1,000 at a time to now get a good idea of what the bootstrap distribution would be for sample means using samples with replacement from the original sample of 25 cars. Okay, and especially we can look here at the standard deviation here, which becomes a good estimate of the standard error of samples of size 25 from this particular population. But also, if we want to get a confidence interval, now we're going to use the two-tailed option here. And if we click that, by default, we get 95% in the middle, and we chop 2.5% off of each tail. And so we see a 95% confidence interval here will go from about 11.83 to 20.18. And anything that's in blue is editable. So if we click on the 0.95 and say, I'd really rather see where the middle 90% is, I get a slightly narrower interval, chopping 5% off of each tail. Or change that to 0.99, and I get a wide interval that takes only 5 values or 6 values off of each tail to get our interval. Okay, so that would be how we would get confidence interval from a bootstrap distribution for a mean. If we'd rather change this to a different parameter like the standard deviation, we can do that and get a distribution of the standard deviation instead, and now we find a confidence interval for standard deviation. Okay, so let's go back to the main menu. Okay. We can do that by sampling for single means, medians or standard deviations, single proportions, difference in means, difference in proportions, or a slope or a confidence interval. In each case, the intervals would, the sampling distribution would be generated by sampling with the replacement from the original sample and calculate a statistic for each sample. Okay, so now we'll move over to the randomization tests.
Okay, so we'll stop it there. I do want to do the other video because that's going to be our topic this week into next week, is confidence intervals. The rest of that video is on hypothesis tests, and we'll play that when we start that topic. So I'm going to start the other video now. And by the way, this other video will explain some of the things regarding confidence intervals that you would not be familiar with at this point. This is the second video that I'll be showing. So I will explain more on Thursday, but I do want you to see these videos because it does use StatKey as the means of coming up with what are called confidence intervals. So let's go ahead and choose this again.
Hi, I'm Patty Fraser-Locke, and this is a brief introduction to Bootstrap confidence intervals. Bootstrap confidence intervals are a way to create confidence intervals using only the data in your sample and some very basic ideas from descriptive statistics. So bootstrapping, key phrase, let your data be your guide. This method was developed by Brad Efron at Stanford University. It comes from the phrase pulling oneself up by one's bootstraps, which refers to reaching down, grabbing the straps on your boots and lifting yourself right off the ground, which seems impossible. It is impossible, and this method seems quite amazing also, I think, the first time you see it. So bootstrapping works because we assume the population is many copies of the original sample. So let's look at an example. Suppose we have a random sample of 6 people. Here are our 6 people, and we're measuring some statistic with these people. Measure maybe the average IQ or the proportion who voted in the last election, or correlation between height and weight, or some sample statistic we're computing from this sample of 6 people. For bootstrapping, we take our original sample and we assume that the population is many copies. So this gives us a simulated population to sample from. So here is our original sample of 6 people. Notice that the simulated population is just these same 6 people repeated over and over and over again, infinitely often. So what does this mean in practice? We sample with replacement from the original sample, since each of these people represents many others in the possible population, using the same sample size, because we're estimating variability here, and sample size is key. So we're taking a sample of size 6 with replacement from this original sample. So let's do that. We sample one person and we get this blonde person, and we sample again, we get the red-headed person. We sample again, we get the blonde person again. Remember, that's possible because we're sampling with replacement and because this person represents many people in the population who have the same characteristic. We sample again, we get this person, or this round person, get the round person again, and finally get this rather scary-looking person. So this is one bootstrap sample starting with our original sample. So again, we assume the population has many, many copies of the original sample. The key idea to see how a statistic behaves, in particular to measure the variability in the statistic, we take many samples with replacement from the original sample using the same sample size. So let's look at an example. What is the average price of a used Mustang car? So one of our students did this, selected a random sample of 25 used Mustang cars from autotrader.com and recorded the price in thousands for each car. So here's a pictorial representation of our sample of 25 used Mustang cars, and there's a dot plot of the cars, and there's the sample size, mean, and standard deviation. Again, this is all your students need to know in order to be able to start constructing and understanding confidence intervals. So our best estimate for the average price of used Mustangs is $15,980 from this sample mean, which is in thousands of dollars. And the question is, how accurate is that estimate? We want some kind of confidence interval or margin of error to put with that best estimate. Key question, how much can we expect the sample means to vary just by random chance? So here's our original sample again. We take a bootstrap sample, which means sampling with replacement with a sample size of 25 from that original sample. And so here's our bootstrap sample. Notice that this blue Mustang car got selected 3 times over here. This gold Mustang convertible did not get selected at all in our bootstrap sample. Same idea, same pictorial as we had before with the 6 stick figures. So here's the idea. We have our original sample, and from that we compute some sample statistic that we're interested in. From the original sample, we construct many, many, many bootstrap samples, doing this over and over again. We compute the bootstrap statistics, same statistic as the sample statistic, over and over again, and we gather all of those into what we call the bootstrap distribution. And because we want to do this thousands of times, we need technology. And so we have developed a set of tools that enable this to be done quite easily. They're freely available to everyone at lock5stat.com. There's another one of these introductory videos that explicitly talks about using StatKey if you want to take a look at that. So let's go to StatKey now, and here is the main menu. Here are bootstrap confidence intervals here, and you get there by going to lock5stat.com. And we're interested at the moment in a confidence interval for a single mean. Notice, however, StatKey has descriptive statistics, confidence intervals, hypothesis tests, sampling distributions, theoretical distributions, and more advanced randomization tests. At the moment, we're doing a bootstrap confidence interval for a mean. Let's go there. There are many built-in data sets connected with our book, Statistics Unlocking the Power of Data. One of them is this Mustang price data set. So let's go there. And you see right here, this area will always have the original sample. And notice that here's the dot plot we saw earlier, although now we can hover over the points and see that this very expensive Mustang car was $45,000. Here's one for $37,900. Some very cheap ones also down here. Here's the sample size, the mean, median, standard deviation, all that we saw earlier. Okay, we're going to generate one bootstrap sample. Here it is down here. Notice that this expensive $45,000 car did not get picked. 2 of these 3 got picked. These 3 of them got picked twice. So this is a bootstrap sample, just as we talked about earlier, sampling with replacement from this data set with sample size 25. We've computed the mean. It's 14.328, and that 14.328 is plotted over here on this area, which will become the bootstrap distribution. So again, this is the original sample. This is the most recent bootstrap sample, the only one so far now. And this is the bootstrap distribution. We generate another sample, and again, we didn't get the expensive one. We got both of these, but not the 2 more expensive than that. These ones we got picked many, many times. at 7 here. So there's 2 7s here and a whole lot here. Again, another bootstrap sample. This mean is 14.484, and now both means are plotted here. We can generate another sample. We get this one, 16.38. We see that plotted here. We can generate another one. 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 You can hover over any of these and see the bootstrap sample that gave rise to that bootstrap statistic, that bootstrap mean. Okay, let's generate 1,000. So there is a bootstrap distribution. We can generate another 1,000 if we want. It doesn't take very long. And again, still hovering over these will show you the bootstrap statistics. So if you watch over here and try not to get seasick, you can see that every one of these gives us one. We can see why these are quite a bit out in the upper tail, and we can see that that's because those bootstrap samples happen to over-sample these expensive cars. Down here at the other end, these small ones are so small because they didn't end up getting these. So you get to talk a lot about randomness and variability in the sample means. These values here, it tells me that I happen to have done 2008 bootstrap samples at this point. Here's the mean of that distribution, and here's the standard deviation of that distribution. And that standard deviation is really 2.134 in this case. It's just the standard deviation of all these 2,000 plus bootstrap statistics. If we go back to the slideshow, here's a previous simulation that we did, and that value, that standard deviation of these bootstrap statistics, is an estimate of the same of the standard error, the same standard error that we can find by formulas also. And so how are we going to So there's 2 ways to find a bootstrap distribution, to use a bootstrap distribution to get a confidence interval. The first way is to use that standard error. So the standard deviation of the bootstrap statistics estimates the standard error of the sample statistic, and a quick interval estimate is to use the original statistic plus or minus 2 times the standard error. So for the mean Mustang price, this original sample mean was 15.98 in thousands of dollars, plus or minus 2 times the standard error that we found from the bootstrap distribution. And we compute that to be 11.624 up to 20.336. There's a second method to use the bootstrap distribution to get a confidence interval. And so let's go back over to StatKey to find that. And actually, let me click one more time here. Instead of using the standard error to estimate the middle 95% from the empirical rule, we can find the middle 95% directly, since we have all of those sample means, bootstrap sample means stored. So now we'll go back over to StatKey. There's a 2-tail button here, and if you click on this, 95% is the default, and it keeps 95% in the center here and cuts off 2.5% from each tail, giving a 95% confidence interval of $11,856,000 to $20,153,000. Very similar to what we found using the other method. We find that both these methods are really valuable. This method is a wonderful visual display that helps students really think about 95% intervals, and the other method kind of sets them up for later on in the course. In Chapter 6, we go back and do the shortcut, what we call the shortcut formulas, and they're all set up to take the sample statistic and add plus or minus something that has to do with the standard error. And so they both really lead them to a deeper understanding of a confidence interval and to what is to come later. Again, the only thing they need in order to get to this point to really understand confidence intervals is being able to read a dot plot and knowing about sample statistics, means, proportions, difference in means, those things. Okay, let's go back to PowerPoint and look one more time at this Mustang prices, and So again, we keep the 95% in the middle, chop 2.5% off of each tail, and always interpret in context. For this simulation, we're 95% sure that the mean price for Mustangs is between $11,930 right there and $20,238 right there. So we keep the 95% of statistics and look at these values to give us the 95% confidence interval. And one more thing before we leave, there's the standard deviation from the simulation, 2.178. You'll get slightly different answers with different simulations. That again is the standard error. And here we show the shortcut formula. This is a sample mean, so the standard error is S over the square root of n. And it's very, very close to what we get with the simulated bootstrap standard error. Okay, let's do a second example. This one is for a proportion. And so this is a poll of likely voters in October 2012, just before the presidential election of 2012. The poll asked 722 likely voters in Ohio who they planned to vote for, and 368 choose Obama, 339 choose Romney, 15 choose otherwise. And we want to find a 95% confidence interval for the proportion of Obama supporters in Ohio. So remember those numbers. In our sample, 368 choose Obama out of 722. If we go back to StatKey, now we want to go back to the main menu. Now we're doing a confidence interval for a proportion. And there's an edit data key. You can edit data. You can enter your own data in any of the options. It's easiest to enter for a proportion because we just need to know that it was 368 out of 722 likely voters. And there's our original sample again. We can generate a bootstrap statistic. It works exactly the same way, same sample size. Now we are sampling with replacement from voters who are picking either Obama or not Obama. And for this particular bootstrap sample, we got 355 out of 722 or 0.492, and it's plotted here. We can generate some more. We can generate 1,000, and we can find either use this standard error there or use the 95%, and we get 0.472 to 0.546 as the proportion, as a 95% confidence interval for the proportion who plans to vote for Obama in October of 2012. Okay. Using StatKey, so here's another simulation, 0.018, almost exactly the same as we had on the previous simulation, and 95% here. We could also use this standard error using the other method. The original statistic is 0.51, plus or minus 2 times the standard error, and we get 0.474 to 0.546, almost exactly the same as we get using the exact 95% of samples in the middle method. Okay, let's do a third example, Diet Cola and calcium. So the question here is, what is the difference in mean amount of calcium excreted between people who drink Diet Cola and people who drink water? So in this experiment, they had 8 people in each group. One of the groups of 8 drank Diet Cola, the other group drank water, and then they collected their urine for 3 days afterwards and measured the amount of calcium in the urine. And the instructions are to find a 90% confidence interval for the difference in means. So we go back over to StatKey and back to the main menu. Now we want to do a confidence interval for a difference in means. And so we get to here. The calcium in Diet Cola is one of the included data sets. So here is the dot plot. Here are the amount of calcium excreted for the water drinkers. Here's the amount of calcium excreted for the Diet Cola drinkers. There's some overlap, although it looks like the Diet Cola drinkers leach more calcium, and that's the question, whether Diet Cola does leach calcium out of the system. So we generate one sample, same method always, which makes it really quite easy for the students to digest. Here we're taking a sample of size 8 with replacement from the water drinkers to get this bootstrap group, sampling with replacement from the Diet Cola drinkers with a sample of size 8 to get this bootstrap group. The means here are 56.875 and 49.25. The difference in means, which is the statistic we care about for this bootstrap sample is 7.63. And we can generate another, generate another, generate another. Again, we're building up our bootstrap distribution on the left there, generate 1,000. And if we do a two-tail, the default is always a 95% confidence interval. But to find a 90% confidence interval, we click on this box here, put in the fact that we want 90% instead of 95%, and there's our answer. We are 90% confident that the difference in amount of calcium excreted between Diet Cola drinkers and water drinkers is 3.375 to 10. Okay. So, why does the bootstrap work? So here is a sampling distribution. We have some population. There is some mean for this population. It's fixed. We don't know what it is. We sample from the population, and there's one of our sample statistics. Notice that it's not the same as mu, but it's not that far off. Take another sample. It's not the same as the first sample, so the students get this idea of sampling variability, and it's not the same as mu, but they're close. Take another one and take a whole lot of them, and we're creating a sampling distribution here so that students see the familiar shape of the normal curve. They're clustered around, centered at mu, and they have a certain variability depending on variability of the original population and sample size. So this is great. We want students to have this image in their head, but in practice, we don't see the tree. We don't know the entire population. We don't see all the seeds. We only have one seed. So there's our one seed. If we're estimating a mean here, that's our sample mean. What can we do with just one seed? And maybe you all repeat in tune with me. We grow a new tree. And that's what bootstrapping is all about. We create the simulated bootstrap population from the sample that we have, and we sample from that simulated bootstrap population. And the amazing thing is we get a sampling distribution that's very similar to the sampling distribution from the entire population. And so there's our sampling distribution. And we estimate the distribution and variability, or the standard error, of the sample means from these bootstrap statistics. There's our mu from the original. And so the golden rule of bootstraps here is that the bootstrap statistics are to the original statistic as the original statistic is to the population parameter. That makes the whole thing go. Thanks for listening, and if you want additional information on bootstrap statistics, you can find it at www.lock5stat.com. Thanks very much.
All right. So that was a lot to digest. And I'm going to break that up to you into smaller pieces over the next 3 sessions. All right. So this week and next week, we will cover confidence intervals. On Wednesday, we're going to use our textbook just for a little part of chapters 20 and 21, which are regarding this thing called confidence intervals. We're just going to use some of the beginning sections. If we went over the entire sections of chapters 20 and 21, we would be doing what typically is done in a traditional statistics course. We would be using formulas, as she had mentioned, formulas to calculate these things called confidence intervals. But we're going to be using StatKey instead. So I wanted to show you a little bit about StatKey. If you're somewhat familiar with StatKey through these videos, and what I mean by that is that maybe you understood 10 to 20% of what she was saying, which is all I figured you would on a first, viewing of that. That's okay, because I'm going to break it apart and show you how it works and give you some of the basic terminology. Now, one thing I do want to mention today before we do our quiz is two concepts that were mentioned in both videos. And they are the idea of sampling with replacement and sampling without replacement. So what do we mean by sampling without replacement? Sampling without replacement means that, let's say you have a group of people, or maybe we can look at it in terms of a container of tennis balls that have different colors, all right? So maybe we have white tennis balls, green tennis balls, yellow tennis balls inside this container. Suppose you put your arm into the container and you randomly select one of those tennis balls, and it'll be one of those colors. Now, sampling without replacement says that once you've selected that one ball, you will leave it out of the container when you're ready to select a new ball out of the container. So you leave it out. And as a result of doing that, you're changing the probability of selecting any of those balls that were originally in there. All right. So, for example, if there was, let's make this easy. Suppose there were 30 white balls, and there were 40 green balls and 30 yellow balls in there. So we know that the probability of getting a yellow ball on the first try is 30 divided by 100, or 0.3. But if we select a yellow ball and we leave it out of the bag, then the probability of selecting a yellow ball on the second try is different. It's changed. It's no longer 30 out of 100. It's 29 out of 99 balls, because we've selected a ball already, and it was a yellow ball. So that's what we mean by sampling without replacement. And in general, whenever we do a survey and we do a random sample of people from a population for a survey, we are doing sampling without replacement, because once we interview somebody, we're not going to just say, all right, we're going to put you back into the population, and there's a chance we may interview you again and ask you exactly the same questions. Obviously, we don't do that. So we do sampling without replacement. Now, what is sampling with replacement? Well, getting back to that analogy with the balls in the bag, it's basically once we select the first ball, we then put it back into the bag, and so it could be selected again. That's called sampling with replacement. And the whole idea of sampling with replacement is that the probability of selecting a yellow ball remains 30 out of 100, regardless of how many times we may end up selecting it, because we put it right back into the bag. So in what we learned today, we learned that in traditional statistics, when we create this, and this is from chapter 19, where we create these things called sampling distributions, we are doing sampling without replacement, right? Because typically it's a survey. We're creating these samples, and once we choose a sample, we're not putting it back in. We choose it, and then we leave it out. But in this other video where they talked about this concept of bootstrap samples, they talked about sampling with replacement. That is, we could end up choosing the same item again when we do sampling. So I just want to keep that in your mind for next time when I describe basically how all of this works. All right, so it's 2:49. In 1 minute, the quiz will begin, and I'll stop the recording. So does anybody have any questions? Again, this was a lot to digest for today, and don't try to strain to try to understand any of this. I want you just to understand some of the little bit of the basics of what they said. And again, it'll be broken down, and we will be using StatKey to construct these what are called confidence intervals. So don't worry about it. And then now it's 2:50. The quiz is ready to be looked at, and you can work on it. Of course, it ends at 3:15, unless you have an extension due to a letter of accommodation. Please do not. This is very important. Do not continue the quiz after time is up. It shows up late, and I will deduct points if you if you decide to work late on it. So please do not do that. All right. A couple of you have done that last couple of times, so please don't do that. All right, that's it, and I will stop the recording, and you may begin.